I brought today a very, at least for me, very interesting topic, which happened actually more or less at the end of my thesis, which I did at Fraunhofer-Institut for the last couple of years. And yeah, actually, I'm very happy to talk about this topic because I didn't tell about these things I did here to a broader audience before. And this is why I'm very happy that you're here today and that you're interested. And it's going to include a little bit of math, but we're going to take it very slowly. It's late in the afternoon, I know, but let's see where we get. So my talk is more or less facing partial shading issues. And I guess most of you might know that partial shading for solar modules is kind of a deal breaker. It comes along with very high losses, over proportional losses. So it's not proportional to the area covered by shade, but due to the nature of electrical series interconnections in solar modules, yeah, well, these losses are quite significant. And what manufacturers usually do, they write on their data sheet some things like less shading loss or quote, excellent hotspot immunity effectively avoids power loss caused by shadow coverage. Very extensive, but in the end, it doesn't tell you anything at all, right? It's not measurable. And this was something I wanted to address, and I wanted to take care of how can we try to, well, squeeze all these different shading scenarios in one measurable number to make it actually comparable. And well, the strategy or agenda for today's talk is something like, okay, we're going to take a look into literature. There is a very nice approach, which I started focusing on more. I want to talk about how we can maybe further develop that idea and tackle it with a Monte Carlo approach. Then we're going to have to take a little deep dive into that equation, which is behind this idea from literature. And then classically, we're going to do a little validation with a simple example and then extend this idea to the application on realistic solar modules, right? So this is more or less how we want to go through this talk today. And well, this paper I read once, it basically says, okay, shading tolerability, let's define this as the average power output. This is what this equation here says. So we're gonna take a look at average power output. My pointer seems to be frozen. Okay, average power output over a couple of scenarios, right? And these scenarios, this group of researchers focused on was to say, well, we see here two solar cells, which are interconnected in series, and we see three different levels of irradiation. We see 1 kilowatt hour per square meter in white. We see in gray 0.5 kilowatt per square meter, and in dark gray 0 kilowatt per square meter, right? And this researchers now stated, okay, let's do all the possible combinations between solar cells and irradiation levels and say, well, this covers infinite shading scenarios, right? We can do that not for 3 irradiation scenarios, we can do that for 1,000 irradiation scenarios between 0 and 1 kilowatt per square meter, and then look at all the different combinations, compute the power output, and do the average power value. And this is actually what we define as the shading tolerability, as it is done in that paper, right? This leads to that equation here. I don't want to go into details. It's also not so important because the nice thing is these researchers showed that this equation, if you increase the number of irradiation steps to infinity, this complex equation here converges towards this very, very simple equation on the bottom. So basically they found, okay, their shading tolerability value is something like 1 divided by 1 plus n, where n is the number of series interconnected solar cells. So this is what they found. This is very nice. This is very simple, but it has some issues. It cannot consider bypass diets. And bypass diets, as you might know, is a very important aspect of solar modules and mitigating these shading losses, right? We cannot do arbitrary solar module layouts. We are limited to this string layout. We can only consider solar cells which are interconnected in series. So these are two things which are limiting me at a certain point, but at the end, it's a very nice and simple equation, right? And we're gonna pick up that idea, and this is what we're gonna talk about a lot today, of these combination of solar cells and different irradiation levels. This is the main idea. But so going towards infinity, what does that mean? If we consider maybe 1,000 steps, which I mentioned earlier, right? And we consider 60 solar cells, which are in a standard module. You see, we're going to end up at 10 to the power of 180 scenarios. So the set of possible combinations is, well, to the power of 3 as large as the atoms in the known universe. So this is kind of a big number and hard to grasp, right? But actually this equation would consider, well, so many scenarios. So the question is, can we learn a little bit more about the set of combinations? And this is, we wanna use this additional information we can learn about the set of combinations to compare it then to our Monte Carlo approach. And well, what do I mean with Monte Carlo? Monte Carlo, as you might know, is we're gonna just do random sampling out of that set, and then we're gonna have a look at this average value. That means the question we're asking ourselves is, how many of these immensely large set of scenarios do we have to compute, maybe by SPICE, so a circuit emphasis-based simulation? How many of these scenarios randomly chosen do we have to compute until this average value of these scenarios is more or less equal to this ST bar value, right? So this is the idea. We want to approach this ST bar value by just picking out random scenarios to not have to compute 10 to the power of 180 scenarios. And we not only want to compare the power output, but we also want to know a little bit more, some more characteristics to be sure that we're doing the same thing. And this is what we want to talk about mainly. And first of all, we're going to take this graph shown in literature. We're just going to toss it away for a second, and I just replaced it by my own graph, which is basically the same, right? So it's the same as done in literature, and we're going to take care for that scenario. As you can see, I already pointed out, so for n equals to 2 solar cells and I equals to 3 irradiation scenarios, we leave out kilowatt hours per square meter. That's not interesting anymore. We can see that there's 6 different scenarios, which I call D, right? So there's D1, there's D3, and D6, which are occurring once, and scenarios D2 and D4 and D5 occurring twice, because it's for a series interconnection of solar cells, it doesn't matter if the first cell is shaded or the second cell is shaded. That's a similar thing, right? So these two are equivalent. So the first more we can learn about this is the characteristic distribution of the average irradiation. So the average irradiation on both solar cells, I just wrote that down here. So of course it's 0 here, of course it's 1 on the other side, and of course it's 0.5 here, where on both solar cells the irradiation is 0.5. And you can see also the values for the other scenarios, right? And you can see we can kind of compute the distribution here. How often do certain values occur, right? This is interesting, and we want to stick to that a little bit. And we can do that. And now we're coming to math, and we're going to be very slow with that. We can use the multinomial theorem for that, or let's say parts of it. And this equation might seem very complex, but you most likely all know about this equation because you know the binomial equation, right? You know a plus b to the power of 2 is a squared plus 2ab plus b squared. And this basically is the simplest case for the upper equation, or the other way around. This equation is the general description of what's happening with these polynomials. And we're going to make use of that equation. And more specifically, we're going to make use of the multinomial coefficients, which I highlighted here, because basically all the information which we need is found inside these coefficients. And we're going to approach that now. So these coefficients give us an information about how often a certain scenario occurs. And these K values here, highlighted in red, they're gonna give us an information on how the scenario looks like, which irradiation value occurs how often. This is hidden in these K values. That means by analyzing these coefficients here, we can basically compute the distribution up here. We're gonna do that for a small example on the next slide. First of all, I want to highlight something different. So if we take this equation and instead of x, we're putting every x equal to 1, you will find that the sum in the brackets is going to become I, so the number of irradiation values we've chosen for our investigation. And we can also see that this bracket at the end becomes 1 also for every possible combination, right? Because this bracket back here is a product of the of x to the power of k, and if we put x equals to 1, well, 1 to the power of something is always 1, and 1 multiplied by 1 is also always 1. So this here becomes 1, which leaves us with I to the power of n is the sum of all the coefficients. And this is important because, well, if this coefficient tells us something about how often a certain scenario occurs, and we know the overall number of scenarios, well, we can compute the probability, right? We can say how likely is it that a certain scenario occurs, and that helps us then later to find how important power values are, right, for that certain scenario. And this is a very interesting thing to know here. So we're going to make use of these coefficients. And the second more we want to investigate, as pointed out already, is the power. I again highlighted that for these 9 cases up here. Obviously, the power in the first case is 0. The power in the last case is equal to 1. And as mentioned before, for example, for that scenario D2, the power is also 0. Why is that the case? Well, we're having 2 solar cells interconnected in series. In both cases, one of the solar cells has 0 irradiation. That means its current drops to 0. And since we're in a series interconnection, that means this solar cell also has a current of 0 ampere. That means the overall power in these 2 cases is also 0, right? And again, we can see, we can kind of compute a distribution of different power levels for all these 9 cases. And this was now very simple, but imagine now this is n equals to 60 and I equals to 1,000. That changes a little bit our, well, capability of just drawing everything out and just writing everything down, right? We can take this equation and we can visualize it a little bit, right? So for this case here we're discussing now, we can visualize it as such a plane where the cases I equals to 0, I equals to 0.5, and I equals to 1 are occurring on the edges, while you can see the other scenarios, D2, D4, and D5 are somewhere in this plane. And I'm going to show you why this is happening, or where you can find this, right? So if you take a close look at this plane, we can see here on this first sketch here, all the coefficients, all 6 possible coefficients for that case are drawn here to the points. We can see the corresponding average irradiation on the edges, 0, 0.5, and 1 again. And this down here is not so important, but it shows you again the scenario, right? It shows you that for an average irradiation of 0.25, this is consisting of an I value of 0 and an I value of 0.5, and both occur once, which is exactly what's happening here in D2. This is the case I wanted to discuss with you, right? Just as a very simple example. So if we now take this coefficient here, 2 over 1, 1, and 0, well, we already know this then leaves us with an average irradiation of 0.25 and with a power output of 0. And if we evaluate this coefficient, that means per definition of that coefficient, we're having n faculty divided by k1 faculty times k2 faculty times k3 faculty. And it's very important to know that 0 faculty is defined as 1. So 0 faculty is not 0. 0 faculty is defined as being 1. That means if we evaluate that coefficient, it turns out to be 2, which is exactly how often this case here occurs, right? And as said before, we can directly, knowing that it consists of 1 times E1 and 1 times I2, we can directly compute that the average irradiation is 0.25. And taking a closer look at this coefficient, because we have sorted the irradiation values from lowest to highest, we know that this here is the lowest irradiation value. It happens once, it is 0, that means the power output for that scenario also is 0, right? And this is everything we can learn just by taking a closer look at this coefficient here. And well, if we're now doing that for n equals to 60, I equals to 1,000, evaluating all these coefficients, all these possible coefficients, we can compute these distributions for I average and for the power for this case. And this is exactly what we want to do later for the validation. So, short break, and what does that mean? In the idea of the paper we discussed earlier, right? We said we're gonna just have all the possible combinations of solar cells and of the different irradiation levels, which means if we want to do Monte Carlo, we're just gonna picking, well, some solar cells out of my solar module, which is sketched up here, and we're gonna just randomly assign irradiation values to these randomly chosen solar cells. And we're going to repeat that a couple of times or many times. And we're going to compute for every single of these scenarios the potential power output using a SPICE simulation. And then we can compare the average power output for that to our ST bar value, so the value from literature. But now we can not only compare the power output, but we can also compare these two characteristic distributions. So everything I explained to you on the last two very extensive slides have the idea of having two more characteristic values to compare between the literature approach and the Monte Carlo approach to be sure that we're doing the same thing here, right? So, and this is now the simple case. We are having 10 solar cells. Yeah, we're taking 10 solar cells and we're going to just randomly assign irradiation values to these 10 solar cells and compute the power output. The question is just how many irradiation values between 0 and 1 should we pick? And if we take a closer look at the equation from literature, and you can see how this equation evolves over I, that means here you can see, well, if you take I equals to 5, then we're going to end up something at this point here. If you take I equals to 10, we're going to end up here, and so on and so on. And this is why I'm always talking about 1,000 irradiation values, because if we're taking 1,000 irradiation values to the power of 10, because we're having 10 solar cells, then we are very, very close to that converged ST bar value, right? So that means we have to split this entire irradiation values to 1,000 different values, and then we are reasonably close to that converged value of the literature equation. And that means, again, we're talking about 10 to the power of 30 scenarios. And the question is now, how many of these 10 to the power of 30 scenarios do we have to compute using a Monte Carlo method? So just randomly picking those scenarios, and how many of those we have to compute until we get to the same value. And this is what we've done, right? So we've taken these 10 solar cells, we divided the scale into 1,000 steps, or 1,001 steps to be more precise. And then we computed and computed and computed until we found this here. So the green line is more or less, let's say, the behavior of the Monte Carlo algorithm. And you can see that already for, let's say, something like 20,000 to 60,000 computations, we are getting very, very stable. So we can expect nothing's happening anymore. That means with a couple of thousand computations, and this took, for that simple case, 3 to 4 hours, if I remember correctly, we are able to compute the same value as the equation from literature does, considering 10 to the power of 30 scenarios. You might say now, well, this is not the same value. It's converged. We agree on that, but it's not the same value. And this is totally right, because, well, in order to work, the literature equation has to take some simplifications into account, right? For example, that, well, the lowest irradiation on a solar cell defines the power output of the entire string of solar cells. This is not happening in reality, right? So this SPICE-based Monte Carlo method is much better computing the power output than just the assumption the lowest irradiation value defines the power output of the entire thing. And one effect here has to do with the fill factor of the entire system, let's say. And I'm not going to go into details with that. This is described in one of the publications we made a couple of years ago. But the message I want to send here is we can explain the difference, right? There is a difference, a total difference in the value we achieve, but we can explain that. We can show you what's behind these differences. That means in the end, what I want to send the message is we are doing the same thing. We're computing the same power output, right? With some difference in physics. And also, if we take a closer look at these characteristic distributions, so you can see in these other two graphs now the distribution of average irradiation, and on the center graph we can see the distribution of the power output. The solid line is for the equation, for the analytical equation, and the data point is for the spice-based Monte Carlo method. And you can see we actually do the same thing, and the differences we can see here. This is exactly where the fill factor comes to place, where it strikes the most. And for this single point here, this is also very simple explained. It's very hard to compute a numerical zero, right? So in the analytical equation, zero is the most common thing to happen, zero power output. But for a numeric simulation, this value zero occurs quite a few times only. This is why this data point is down here and not up here as it should be, but that's not very important here, right? So we can do that, right? We can take Monte Carlo method, just picking out random scenarios, and we can do the same thing as another equation did in literature. How does that now help us for our problem of solar modules in the field and partial shading in the field? Well, there's one issue with that, what we did so far. These scenarios here, if you remember, or if you think back to the images I showed you on the first slide, they don't really look like partial shading looks like if you consider your solar modules on your roof, right? Just grabbing these random cells, this is rather like dirt or dust on your solar modules, but not what we talked about with partial shading. Partial shading rather looks something like this. Could be such random shading clusters, could be rectangular shades as shown down here. This is the much more interesting thing, and this is what we want to address. And again, Monte Carlo helps us, or looking at the sets, this set omega zero. This is the entire thing, right? This is all the possible combinations of solar cells and irradiation values. And somewhere in this immensely large set, there are these subsets, these cases, where these randomly chosen solar cells just conveniently align to form a specific geometric shape, right? You agree, hopefully, with me that these subsets exist somewhere in this immensely large set, and these are these omega 1 and omega 2 sets. These are the ones we're interested today. And the nice thing is we don't have to know something about them, right? We are only interested in the average power output. So we're going to do the same thing as before. We're going to have those rectangular shades. We have those clustered shades. We're going to say, well, we just do random sampling. And when we have a converging power output for, I don't know, 1,000, 2,000 or 3,000 scenarios, then we say this average power output describes the average power output of the entire set. And therefore, well, in general, what's happening when we have such random clusters, or when we have such rectangular shades. That's the main idea behind all of this, right? And we are doing this now not for 10 solar cells, but for realistic solar modules. And we did that for 4 different modules. Well, you all know how modules looked like until a couple of years ago. These were these 60 cell with full square solar cells. We're having today's shooting stars. So every module today looks like this. We call it a butterfly layout. So it consists of 120 cascade cells, maybe today 150 or 180, but in principle, this layout is the same, right? And then we're having 2 shingled solar cell layouts. These are a little bit more special. I cannot go into detail today what's behind all of this, but this is now the first time my company also pops up. because we are doing this very special shingle matrix interconnection. It looks a little bit like a brick wall. This is one thing I can tell you about it, but much more I'm not going to addressing today. The thing is, we are taking a close look at this also because this is what we are doing at our company. And we're going to take those 4 module layouts and we're going to compare those for these clustered shadings and for these rectangular shadings. And if we do so, this is what we find. We see here on the left-hand side the Monte Carlo result for a rectangular shading. We see on the right-hand side the same thing for random shading. And we see in the blue, in the greenish colors, the 2 shingled layouts, and we see the butterfly layout here in red and the conventional layout here in red. And you might now say, oh, well, how convenient that the shingle matrix layout performs best in this investigation. And he tells us now everything of this, what he told us the last 25 minutes. But the thing is a little bit the other way around. Our company is doing what we're doing today because a couple of years ago we found these results. And we said, well, this is looking really promising, and let's focus on that technology, and let's commercialize this technology. This is based basically on these, not only, but also on these findings. So the causality is a little bit the other way around. But what's important, we can quantify by Monte Carlo, by just randomly sampling, we can quantify the shading resilience for solar modules, and we can make it actually comparable, not considering 10 to the power of 180 scenarios, but only a couple of thousand if you look here down on the x-axis. And that's the very interesting thing. These computations, they take on just a standard desktop computer, they take about, well, maybe a day or maybe 1.5 days for these more complex layouts. So this is computable, right? You don't need a supercomputer to do that. You can do it on your computer basically at home. And with this, I want to summarize the ideas I presented to you. So we started off with that very complex looking equation from literature. I hopefully showed you in an understandable way how can use the multi-nominal theorem to dig much deeper into that equation and the idea behind that equation. And we, of course, applied this entire idea on realistic shading scenarios with realistic solar module layouts. And well, we are doing shingle solar interconnections, more specifically shingle matrix interconnections. So we are very convinced that when it comes to partial shading, for example, on your building, a shingle matrix module is more or less the best you could do in order to mitigate losses from partial shading. And with that, I'd like to thank you for your attention. Once again, I'm very sorry for the delay in the beginning, and I can answer a few more questions and then need to head back to my private emergency. I'm again very sorry for that, but yeah, you can see my contact here. If there's more questions arising later, just take a screenshot or look in the video later on and just write me an email. Thank you.
Thank you again so much as well for your presentation. It's very interesting. Like you said, we also only have maybe 5 minutes to answer quickly some questions. So if anyone has any questions, please feel free to either unmute yourself and ask them directly or write them in the chat box. And I hope also for everyone that the voice was clear as well, that you could hear everything clearly. Yeah, hopefully that was not an issue.
Maybe I overdid it with the math so late at the day, but I want to be really honest. It was a lot of fun when this started to click, right? So when I found this way to tackle this equation, and I never told somebody, so you had to sit through this together with me today. I at least enjoyed it a lot.
Yeah, I think it's quite technical, as in.
It definitely is. It definitely is. So I pitched that talk to my fiance, and she was like, "Yeah, okay."
Yeah. Yeah, we have many people from the field, like directly in the solar field. That is why. Yeah, I thought the topic would be fine and understandable, I hope, for everyone. We have here one question from Narciso. Is there a software where we could simulate this and hopefully skip doing the math from scratch?
Skip the what?
Is there a software where we could simulate this and hopefully skip doing the math from scratch? That was the question.
I wish I could say yes. That I would have been so no. So to make it short, no. I didn't put everything of this into a library. I'm not a very trained programmer, so this code ran during my PhD, but I never made it to publish a library where you can just use the function. But yeah, it maybe takes a little, but it's, in my opinion, not extremely hard to understand. So it's not rocket science what I did here, right? It's you need to give it some time, right? It took me several months to figure everything this out. I not told you this in 20 minutes. Obviously it seems like a lot, but it actually is quite comprehensive, and then it's actually also quite easy to redo, let's say. But yeah, not without having to code something. No library. I'm very sorry.
Mm-hmm. We also here have a question on why choose Monte Carlo and if there is another option to do the same.
This is a good question. So I read a couple of papers on what different methods to use here. So actually, I combined Monte Carlo with something like the what was it called? I combined it with a special sampling method to equalize the set of, or the let's say the to equalize the space, to have to not just randomly pick values, but to have the random chosen spots distributed evenly on the entire search space. It's some hyper sampling, or I'm very sorry, I just forgot the term here. And what I read from the papers was that for this special application I wanted to do, Monte Carlo is a reasonable thing. And I talked to a mathematician about this, also not my complete background. And he said, well, that's totally fine. You can compute that within a couple of hours to 1 day or 2 days. He wouldn't change something about the method. But if you're really into mathematics, there's probably more ways to do that. The basic idea is not to having compute so many scenarios, but just some of those scenarios to end up at a reasonably good approximation. That is the long answer I can give. I know that didn't completely address your question. I'm sorry, but that's the best I can do right now.
Thank you for your answer. And we have one final question from Adham. Is a single type mod, this will be the final question, so we can wrap up the webinar. Is a single type modules widely available commercial wise nowadays among all suppliers?
Not widely. It's still, let's say, a niche product. At least, let me jump back, at least the shingle string layout. So not the one we are focusing on, but the other shingle layout, you can get products on the internet, right? The shingle matrix. So we're gonna install the first machines. We are an equipment manufacturer. So our customers are module manufacturers. So we are now installing the first equipment. That means we guess that the first products with the shingle matrix layout maybe will come start of next year, once the manufacturing side is running. It's currently being built. And for the shingle string, there's, for example, Tongwei, there is Solare, SunPower from the US. They're having some products. And if you go onto the internet, you will find, especially in the camping area, so products for camping and outdoor, there are some no-name Chinese manufacturers which also will sell you some shingled modules. But if you look for some names, for some larger brand, it's gonna be Tongwei, Solare, and Maxeo and SunPower. These are the most common ones.
Mm-hmm. Okay.
I actually saw such modules in Freiburg on a rooftop. So shingled modules are already happening, but you have to really carefully look out.
Sounds good. Yeah, again, thank you very much for your presentation, for answering all these questions. I will leave here your email for anyone. If you have any further questions, then you can ask them maybe in the email that you can find here in the chat box. Yeah, again, thank you for your time and for accepting to join us in today's webinar. And also thank you for all the audience that was with us today as well. You can find
Thank you so much, and thank you for the invitation. It was my pleasure.
Thanks a lot and have a nice afternoon. Goodbye, everyone.